Okay, let's continue on the hydrogen atom. Now let's go to the quantum mechanical picture of this atom. In the previous video, we found the transitions of the electrons, right, when we have different states, correct? Imagine that this is the case for hydrogen, and we are in the visible. Remember, the visible hydrogen goes from the second level, which is n equals 1, n equals 2, correct, and so on. Imagine that it goes in this way. We have emission. So actually, the origin for these spectral lines that were discovered, remember in the previous video by Fraunhofer, is coming from the transition of the electrons among these levels, right? If we have the spectrum right here, or let's say that's for hydrogen, but actually these spectral lines are coming from these transitions, correct? That way. And that's the origin for these spectral lines. This is a spectrum found by Kirchhoff, right? We have, remember, two types, continuous, emission, and absorption. And this is absorption. So in this case, it's emission, right? These are the frequencies for hydrogen represented by these transitions right here. Okay, perfect. Now let's go to this analysis. At the beginning, when we're dealing with hydrogen, hydrogen deals only about, in case of Bohr's model of the atom, hydrogen, it works only with one quantum number, and this is called the principal quantum number, right? But later, using techniques, new techniques, is found that we need more quantum numbers to represent the state of the electrons of the atom, in this case hydrogen. Great. For example, if we have this energy level, right, the principal lines, if we place that line and we use a high resolution spectrometer, is found that more lines are split from this single line, right, from the principal line, correct? So we have three more, or four, or two, depends on this level. Could be 1, 2, 3, and so on, correct? But again, using the high resolution optical spectrometer, more lines are found to be right present in this spectral line. So means what? That we need another layer, another number to represent the new findings, correct? And we represent this by L. And this is called the orbital quantum number, correct? Because the electron is supposed to be moving around the nucleus, correct? Moving around the nucleus. So it presents a characteristic which is called the angular momentum. Any object moving in circular path, right? It has angular momentum, and angular momentum must be conserved. We use angular momentum, energy, because they are conserved. Correct? Perfect. That's why this quantity is very important in physics. Angular momentum is important because it's conserved. Perfect. Now, we have different types of orbit. We can have very elongated, right, orbit like this one. You simulate kind of a particle moving right back and forth, back and forth. In this case, it just barely rotated, moving in the circular path, right? That's why we take this to be angular momentum equals to 0, or close to 0, right? Because it's very elongated ellipse, let's say. Later we have different orbit, elliptical orbit, correct? And angular momentum is 1. And when we have a circular, that's the maximum angular momentum possible, correct? It's gonna be L equals 2. So the maximum is when it's circular, that's the maximum angular momentum. If we have more orbital quantum number, the maximum is gonna be the circular one. Could be 0, 1, 2, and 3, but the third one is gonna be the circular one because that one has the maximum angular momentum, the magnitude, correct? Perfect. Later, these lines were placed into a strong magnetic field. And it's found that this line also split in more lines, into more lines, correct? So we need then another number to represent the new lines, right? And that is called then the magnetic quantum number, because the spectral lines right here are placed in a strong magnetic field, and we have more lines. Right? Perfect. And these are represented with the orientation of the magnetic of the angular momentum. Remember, every time we have an object moving in circular path, any object moving in circular path, we associate this motion with angular momentum. Correct? The moment. Also, we can change the orientation. If we change the orientation, also we change the momentum, because angular momentum is a vector. It has magnitude and it has direction. Right? This quantum number is related to the direction, to the orientation. Could be in this direction, or could be, imagine, right in that direction, or could be rotating right in that direction. Correct. So we have an orbit, right, can be changing, right, the orientation, so we change the angular momentum. Correct. And according to Bohr's statement, the angular momentum, right, is given in this way. Remember, angular momentum is quantized, so it's equals to a whole number of h, the Planck's constant, divided by 2 pi. And it's represented in this way. Actually, this is right the orbit. Or we have an orbit right here, another orbit right here. Correct. And this is the direction. Also, we can represent in this way. Look. Correct. And it's kind of rotating the spin and so on. Okay, great. Perfect. Now we were right here. And later, these spectral lines were placed into, again, a high-resolution optical spectrometer. And it's found that each line presented 2 lines, right? These 2 lines are in each of these lines, so means that we need another quantum number to represent the new lines. And now this is called the spin quantum number, because it's only two cases, up and down. Let's call it up and down, right? Imagine that is the rotation of the Earth, because the Earth is rotating right at the same time it's spinning. In this case, is the spinning of the Earth. This is like, let's say, the rotation of the Earth is gonna be like a spinning. We see relate this to the Earth. Correct? And we have the spin quantum number. We have only 2 options. It's gonna be up and down. Correct? And with these new numbers, we describe now the atom of hydrogen. Correct? Perfect. Now let's go to more information on this analysis. Let's go to the shells and subshells that we also use to represent these quantum numbers. Okay, let's do all the behavior of the atom, right? Atom of hydrogen. Perfect. So we have the principle one more time. Principle quantum number. Remember the symbol is N. And also this is quantum number. Also these are called the shells. Current symbol is N. And N can take any value from 1 to infinity, but according to our periodic table, it goes from 1 to 7. Right? So N usually goes from 1 to 7. 6, 7. You can take more values, of course, but the maximum in the periodic table, we have 7 period is gonna be N equals to 7. Okay, great. And then we have the subshells. Correct? Right here, this is principal quantum numbers, the shells. Now we have the subshells. And this is, the symbol is L, correct? The orbital quantum number, and we have these values. L equals to 0, right? 1, 2, 3, the maximum is 3. Also, we can go to 4, correct? And these are the letters representing these orbitals. This is S, P, D, F, and we can use this as G. We can use more like I, H, I, and so on. Perfect. And then what do we have? We have the orbital types. Orbital types. Correct. Then we have one more time S, P, D, F, G, H, and so on. Correct. Each one has this number of orbitals. It has 1, 3, 5, 7, 9, right, and so on. Correct. Perfect. And each one has, this is a numbers of orbits, right? Orbit. Right, and also we have electrons. How many electrons for each orbit? Well, it's gonna be 2. It's gonna be 2, 6, 10, 14, 18, and so on. The maximum numbers of electrons for each orbit. Okay, perfect. Now let's go again and see how are these related. They are related in this way. Perfect. We have first the principal quantum number, right? Quantum number, correct? It's gonna be, let's represent this quantum number, okay? Gonna be N, that's the symbol, correct? And it goes from where to where? N is equals to 1, 2, 3. Remember, it goes to 7, up to 7 using the periodic table, correct? 4, 5, 6, 7. Of course, you can take more values. And then principal characteristic is the energy, right? N is equals to, because we're dealing with hydrogen atoms, gonna be negative 13.6, which is the ground state, correct? Times z squared over n squared. Perfect. Now let's go for the second one. The second one is gonna be orbital quantum number, right? Orbital or quantum number. The symbol is L, correct? And L, now take these values. L is equals to 0, 1, 2, right, until n minus 1. And this is the magnitude. The magnitude is gonna be, let me do right here. L is equals to the square root of L times L up plus 1, right? H over 2 pi. This is the magnitude of the angular momentum for the electron, right? Magnitude. This is the magnitude, right, of angular momentum. Angular momentum of hydrogen. Okay, perfect. Let's go to the third quantum number, which is the magnetic quantum number. Magnetic quantum number. The symbol is gonna be ML, correct? And well, these are the values taken by these quantum numbers. Gonna be from negative L, negative 2, negative 1, 0, 1, 2, correct? 2 plus L. Correct. And there's gonna be the component in the z direction is equals to ml times h over 2 pi. Correct. What is the meaning of this? Well, it was represented in the previous section right here. Remember, it's similar if we have a compass. we have a compass, and we place this into a magnetic field, what happens? Well, the compass, the needle is gonna be oriented, right, according to that magnetic field, correct? Imagine that we have one more time a compass. Imagine this is the direction of the compass, and we place this into a magnetic field. Imagine this is the external magnetic field. So what happens? Well, this needle is gonna be moving. Imagine that this is not so strong, this magnetic field, the external magnetic field. Imagine it goes by like changing, it's oriented according to this direction, correct? And that's represent again this orientation. Imagine this is Z direction, this is Z. So it's gonna be the component. What should be the component? Well, the component is gonna be, we break this into component, right? One in this direction, one in that direction. It's gonna be this component. Correct? And it's represented in this way. Of course, if we increase the intensity, right, of the magnetic field in the Z direction, later it's gonna be right parallel to that direction, and so on. Correct? That's the idea for this component in the Z direction. Usually we do this in this way. This is Z, right? Z direction, right? And this is, for example, the direction, correct? And what should be Z direction? Gonna be now LZ. This is the angular momentum, correct? And this is the component in the Z direction, correct? Using the angle theta, for example. Again, if we increase the intensity of the angular momentum, this needle, right? Imagine it's a compass one more time. It's gonna be more and more parallel to the magnetic field, right? In that way. Got it? Okay, perfect. And finally, we have the spin quantum number, right? The spin quantum number. We can use MS. It has only two possibilities. It's gonna be plus 1/2 and negative 1/2, or up and down. It's the same meaning. Okay, perfect. Again, this is another way how we can describe the hydrogen atom. Perfect. Now let's go to the case when we have multi-electron atoms. This is again only one electron, or atoms with one electron, right? Now what happens when we have multi-electron atoms? Let's do it. In this case, we need to represent all these electrons, right? And to do that, we use the electron configuration. But before that, we are again in multi-electron atoms. Multi-electron atoms, right? And we can use the same form for the hydrogen electrons to go to multi-electron atoms. Okay, perfect. But there are some differences. These are the differences when we're going from the picture of hydrogen atom with one electron to atoms with more than one electron. Correct? And these are some differences. One is that the values of the electron energies are different for different atoms. Two, the electron probability clouds, because now when we're dealing with multi-electrons atoms, and also we apply the Schrödinger equation, the electrons are represented as probabilities, right, as clouds of probabilities. And that's the statement right here. So what do we have? The electron probability clouds varies from element to element to element. And three, each quantum state, this is very important, each quantum state can be occupied by only one electron. Only one electron. And this is called the Pauli principle, Pauli exclusion principle. This is called the Pauli exclusion principle. Only one electron, I can be in one quantum state. Okay, perfect. Remember, the quantum state is represented by one quantum state represented by N, L, MS, MR, and MS. Right? That's the state. Remember in thermodynamics how we represent the state? How the state is represented in thermodynamics? We have what? In thermodynamics, we have what? We have pressure, volume, temperature. Right? That's the state. In quantum mechanics, what is the state for the atoms? And I'll be represented by N, principal quantum number, right? Orbital quantum number, right? Magnetic quantum number and spin quantum number. Got it? Okay, perfect. Great. And this is again called the Pauli exclusion principle. Yes, okay, now let's see what happens when we have multiple electron atoms and want to represent all the states. Well, it goes in this way. It goes in this way. This is the way how it's represented. In this case, we have the electron configuration, right? Electron configuration to represent this any element. In this case, we use the principal quantum number and the orbital quantum number. For example, imagine that we have this case. We have 2p5. This number represents the principal quantum number. Okay, this is principal quantum number, and this p symbol represent the subshell, right, or the orbit, right, subshell or orbit, and this represent the number of electrons, correct? Number of electrons in that subshell, electron, number of electrons. Again, this is the electron configuration. We have also this arrangement for the state. The first one, the ground state, we have 1s. In the second one, the second energy level, we have 2s and 2p. In the third level, we have 3s, 3p. What is the next one? Remember, we're dealing with s. By the way, look, we have s, p, d, f. We can use more, f, g, h, i, and so on. But this is the most important one. This s stands for sharp. When we're dealing with lines, it's very sharp. This stands for principal. This stands for diffuse. Diffuse. And this stands for fine spectral lines. Actually, it's related to two ends are related to p, or the principles are related to magnetic quantum numbers, because they're very fine, right? Very close, very fine. This is with ms. Okay, that's the origin for these letters. Okay, perfect. Now we are right here again. We are SP D 3D. The next one's 4 S 4P, correct. 4D. And what is the next one? 4F 5, right? 5S. What else? 5P, 5D, 5F. We can use one more 5 what? FG, correct. The next one gonna be 6S, 6P, 6D, right? 6F. We can use more if you want to. Remember, the maximum for our periodic table is gonna be F. But we can continue right here. Gonna be 6G, right, and 6H if you want to, and then 7S, correct. 7P, 7D, 7F, okay, 7G, and so on. And finally 8S, right, 8P, 8D, 8F, 8G, and so on. And this is the way how we work with this orbital, right? This is the first one, right, and so on. These are parallel in this way. They're going in this way. Can you see it? In that way. And it goes in this direction. Correct. So for example, we start with 1S. Gonna be 1S. The next one gonna be 2S. Right, the next orbital 2P. The next one 3S. Then we start again with the next one, 3P, 4S, right? And the next one, 3D. Correct, what else? 4P. What else? 5S, right? And so on. Got it? In that way. For example, if we have sodium, right? Imagine that we have sodium as an example, right? Sodium has 11 electrons, right? Our atomic number is 11. So how to represent this element using the electron configuration? Well, it's gonna be 1s2. Remember, it's the maximum for S. The maximum is 2. For P, the maximum is 6. For D, the maximum is 10. And for F, the maximum is 40. Okay. So do we have gonna be right here. The next one gonna be what? 2s2. The next one gonna be 2p6, gonna be 10, and the last one is gonna be only 1. Correct. Also, we represent this in this way. If this is the ground state, n equals to 1. Correct. And what do we have in this state? Well, we have this 1s1, and we have that this is spin up and spin down. We have only two electrons. Correct. For n equals 2. Okay, for n equals 2, what do we have? This is the level right here. And in this case, we have 2, right? Two orbitals. Correct. It's gonna be 2s1. Well, 2s2 actually. Spin up, spin down. We have the next one. It has 6. This one has 6. Correct. Gonna be 1, 2, 3, 4, 5, 6. This is 2p6. And we have the last one, n equals 3. And for that one, we have only what? Only 1 electron. It goes right here. It's gonna be only 1 electron. It's gonna be 3s1. So again, we can represent this electron configuration in this way too. Correct. And this analysis of the quantum theory, we explain, or the periodic table is explained by using this electron configuration and taking the base of the hydrogen atom. Okay, perfect. Well, with this we finish this chapter. Remember, we are by chapters in this series of videos, and I'll see you in the next chapter. Okay, thank you. Bye.